Hey there everyone. So let's get ready to do some lengthy derivations directly from Econometrics. So yes, in front of you is a question directly from previous year, i.e. is paper 1, where you have been given a two variable linear regression model yi is equals to alpha plus beta xi plus ui. As you know that yi is the dependent variable which depends on the independent variable xi, and alpha and beta are the parameters, and ui in this model is the unknown disturbance, right? Means all the other variables which can have influence on the dependent variable but not considered in the model are under the unknown disturbances, that is ui. Now in the question you have to calculate parameter alpha and beta by the OLS method, and not only that, along with it you have to estimate the standard error of these estimates. So basically you have to calculate alpha hat and beta hat, as well as you have to find out the standard error of alpha hat and standard error of beta hat. So let's begin with our OLS problem of estimating alpha and beta. Okay, right. So initially, now we know that the estimated value, that is yi hat, is equals to alpha hat plus beta hat xi, right? And the actual value is basically this estimated value plus the error of estimation, right? So yi is equals to, what is this alpha hat? This is the thing, and along with that we have our error of estimation. So yi is equals to yi, okay, in place of this we can substitute this, that is alpha hat plus beta hat xi plus ei. Now here what is the problem? So basically our objective here is to minimize this, okay, minimize this error of estimation, because obviously the more the estimated value is close to the actual value, the proper is your estimation. That means you have to reduce your error, right? So therefore ei is equals to yi minus yi hat, right? Or ei is equals to yi minus alpha hat plus beta hat xi. Now I'm going to take square and summation of this error term, that is ei square summation I is equals to 1 to n. So that becomes summation I is equals to 1 to n yi minus alpha hat plus beta hat xi whole square. So now my objective is to minimize this square of error estimation, right? So first order condition of minimization is what? Delta summation ei square by delta alpha hat, okay? Because I'm going to estimate the value of alpha hat for which the error is going to be minimized. So this should be is equals to 0. Now, let's say this is equation 1 and I have to differentiate equation 1 with respect to alpha hat. So what do I get? Is equal, this implies 2 summation I is equals to 1 to n yi minus alpha hat plus beta hat xi into minus is there, right, with the alpha hat, so I have minus 1 here, okay? This is equals to 0, or summation yi is equals to summation alpha hat plus beta hat, sorry, minus beta hat summation xi. So I can say this is equation number 2. Again, I have another parameter, that is beta hat. So I'm going to estimate that so that it will also reduce or minimize the error of estimation. So delta summation ei square by delta beta hat, that is equals to 0. That means I have to again take the derivative of equation 1 with respect to beta. So what am I going to get here? Here I'm going to get the following result, that is 2 into summation yi minus alpha hat plus beta hat xi into, since I have beta xi, so I will get minus beta hat here, right? Sorry, minus xi. Minus xi. That is equals to 0. So now let's simplify this. We get summation I is equals to 1 to n xi yi is equals to alpha hat summation xi plus beta hat summation xi square, right? So this is equation number 3. Now equation 2 and 3 are also called normal equations, okay? Equation 2 and 3 are called normal equations. Now again from the second equation, let's scroll up. Let's write down the second equation, okay? That is summation yi is equals to summation alpha hat plus beta hat summation xi, and try to calculate or estimate the value of alpha, that is alpha hat, okay? So equation 2 is summation yi is equals to summation alpha I plus beta hat summation xi. Now let us divide both sides of the equation by n, okay? So 1 by n summation yi is equals to 1 by n summation, okay? This is not alpha I, this is the estimate, that is alpha hat, yeah. Summation alpha hat plus beta hat summation xi by n. So now this is our y bar. This is n times alpha hat, so n alpha hat by n, and n gets cancelled, and this side it is beta hat into x bar. So from here we have our estimated value of alpha, that is alpha hat is equals to y bar minus beta hat x bar. This is the estimated value of alpha hat. Let us highlight it and mark it as a star equation, okay? Right. Now let us rewrite equation 3, that is the normal equation 3 again, in order to estimate beta hat. So third normal equation, the second normal equation is summation xi yi is equals to summation alpha hat xi. Let's just scroll up to recheck the values. Yes, so plus beta hat summation xi square. Now from here let us put the value of alpha hat from the star equation, that is the estimated value. So we have summation xi yi is equals to y bar minus beta hat x bar summation xi plus beta hat summation xi square. Let's open the bracket, expand. So summation xi yi is equals to y bar summation xi minus beta hat x bar summation xi plus beta hat summation xi square. Now let me take the y on the left side. So I have summation xi yi minus y bar summation xi. And on this side, let us take beta hat as common. So we have got summation xi square minus x bar into summation xi. So therefore beta hat is equals to summation xi yi minus y bar summation xi whole divided by summation xi square minus x bar summation xi. Let's try to simplify this. Okay, first let us denote uh, let's work with the numerator. So let us say 1 by n summation xi yi minus 1 by n. Okay, you already have y bar into summation xi, correct? Whole divided by, again same goes for here, 1 by n summation xi square minus x bar into summation xi by n. So basically I have divided n with the numerator as well as the denominator. So the simplified value is beta hat is equals to 1 by n summation xi yi minus 1, sorry, minus, so this is y bar, and 1 by n summation xi is x bar, divided by, this is 1 by n summation xi squared minus, this is x bar into x bar, so x bar square. So it's very clear. So this is the estimated value of beta hat. To write it down specifically, this is our covariance and this is the variance of x. So that means I can also write down beta hat is equals to covariance of x comma y by sigma of x square, right? So this is our second estimate. There's another way of writing it down. So let me just show you. That is using the sum of deviation, right? So this is covariance. So another formula for covariance is 1 by n summation xi minus x bar into yi minus y bar. Divided by, similar, same goes for the variance, that is 1 by n summation xi minus x bar whole square. Now let us take these deviations and denote it with small alphabet, right? That is, let summation xi minus x bar is equals to small xi. Okay, not summation, only the deviation I need to say. Yes. And yi minus y bar is equal to small yi, correct? Then what can be the, how can I write beta hat? So the estimated value of beta hat is equals to 1 by n summation small xi into yi by 1 by n summation small xi square. So this gets cancelled and summation xi yi by summation xi square. Now this is the estimated value of beta hat using OLS estimator, right? Now let's move on to the second part of the question, right? Let's scroll up to look at the second part. So the second part of the question, they have asked you to estimate the standard errors of these estimates. So let me start with the calculation of standard error of beta and then I will solve alpha, okay? Okay. Right. Now let us write down. So variance of beta hat, right, is equals to expectation of beta hat minus expectation of beta hat to the power square. Now since expectation of beta hat is equals to beta, right, from property of blue, that is unbiasedness, therefore variance of beta hat is equals to expectation of beta hat minus beta whole square. Now again, from the proof of property blue, that is the Gauss-Markov theorem as well, so we know that beta hat is equals to beta plus summation ki ui. That means beta hat minus beta is equals to summation ki ui, right? Now if I take whole square and write down the expectation in the next line, that is E of beta hat minus beta whole square, then it is equals to E of summation ki ui whole square, right? Now, so whole square, what is the whole square formula here that we can write down, we can expand it. So that is equals to summation ki square ui square plus summation I naught equals to j ki kj ui uaj, and of course this is, here is the estimated term. Now here we have summation expectation of ki square ui square plus summation ki kj expectation of ui uj. Now from the property of unknown disturbance, we know that the covariance between ui uj is 0, so this value is 0. That means I have expectation of beta hat minus beta whole square is equals to summation ki square into expectation of ui square plus 0. Also, the variance of the unknown disturbance is sigma u square. So that is summation ki square sigma u square. That is expectation of beta hat minus beta whole square. Now from next line, instead of writing expectation of beta hat minus beta whole square, I will simply write down variance of beta hat that I am actually calculating. Now this is equals to sigma u square summation ki square. Now again, while we were proving the blue property, that is the unbiasedness property, there we have already got that the value of ki is equals to xi square by summation xi square. Sorry, xi by summation xi square. Okay. Right. Now, so I can put this value here. So what will happen? Variance of beta hat is equals to sigma u square summation xi by summation xi square whole square, right? So that means variance of beta hat is equals to sigma u square summation xi square by summation xi square whole square, right? That means I can cancel this and this term. So what I'm left with is variance of beta hat is equals to sigma u square by summation xi square. Now what is the standard error? Standard error is, so standard error of beta hat is equals to root over variance of beta hat, that is equals to sigma u by root over summation xi square, and that is the estimate of standard error of beta hat. Now for alpha hat, again we have to find out the variance and then the standard error, right? So from the property of blue, that is the linearity property of blue, okay. So before that, I'm going to write down the value of alpha hat, which we have calculated by the OLS method. That is alpha hat is equals to y bar minus beta hat x bar, okay. Now from the linearity condition of property blue, we have value of beta hat is equals to summation ki into yi, right? Now if we put this value of beta here in the value of alpha hat, then we have alpha hat is equals to y bar minus summation ki yi into x bar. Now again here alpha hat is equals to then what? 1 by n summation yi minus ki x bar summation yi. So alpha hat is equals to, if I take summation 1 by n minus ki x bar into yi, right? So alpha hat can be written in this form. Now next step, so I have to calculate variance of alpha hat. So variance of alpha hat is equals to variance of this whole thing that we have got, summation 1 by n minus ki x bar into yi, right? So I can write it down as this summation 1 by n minus ki x bar variance of yi. Now from the property of the dependent variables, we know variance of yi is equals to sigma u square. So we can substitute the value there. So we have variance of alpha hat is equals to summation 1 by n minus ki x bar whole square into sigma u square. Again, variance of alpha hat is equals to sigma u square summation. Now this is whole square formula. Let us expand it using a minus b whole square. So this is 1 by n square minus 2 ki x bar by n plus summation, no, we are not adding summation now. So just the b square, that is plus ki square x bar square. Yes, so this is the expanded term, right? Now in the next line, variance of alpha hat is equals to sigma u square, summation of 1 is n by n square minus 2 x bar by n summation ki plus x bar square into summation ki square. Now again from the past derivations, okay, of the Gauss Markov theorem and the property of blue, we have certain values. What are the values? So we have the value for summation ki, which is equals to 0, and the value of ki is equals to xi by summation xi square. So therefore summation ki square is equals to 1 by summation xi square. So this we have already proved above while we were estimating the standard error of beta hat. So from there also we can put this value directly. But anyway, we know these values. So let us just put these values. So the simplified version is variance of alpha hat is equals to sigma u square. Now n by n square, so 1 by n minus, this is now what? Summation ki is 0, so 0 plus x bar square. Now this summation ki square is what? Summation xi square, right? So therefore variance of alpha hat is equals to sigma u square 1 by n plus x bar square by summation xi square. Now let's take the LCM. Okay, so we are going to simplify it further. Now variance of alpha hat is equals to sigma u square summation xi square plus x bar square by n summation xi square. Now here this, since summation small, sorry, not take summation here, only xi, okay, since what is the value of xi? Small xi is the deviation from the mean, that is xi minus x bar. Let us put this here, that is variance of alpha hat is equals to sigma u square summation xi minus x bar whole square plus x bar whole square, right, divided by n summation xi minus x bar whole square. Now let's simplify again, expand. So variance of alpha hat is equals to sigma u square summation xi square minus 2xi x bar plus x bar square plus x bar square by n summation xi minus x bar whole square. So this is equals to again sigma u square summation xi square minus 2 x bar summation xi plus summation x bar square plus x bar square divided by n summation xi minus x bar whole square. Now this is equals to sigma u square. Let's simplify again. So this whole thing is divided by n. So let us just divide by n, right? So 1 by n summation xi square minus 2 x bar square plus 1 by n. So this n gets cancelled, so it is only x bar square plus x bar square divided by n, no more n because n is cancelled here, n by n. So we have only summation xi minus x bar whole square niche downwards. So as you can see now is equals to sigma u square 1 by n summation xi square minus 2x bar square. So these two adding up to 2x bar square again. So this gets cancelled. Now in the denominator I can write down the small letter xi square again, right? So the simplified variance of alpha hat is equals to sigma u square into 1 by n summation xi square by summation small xi square, right? So standard error of alpha hat is equals to root over variance of alpha hat, which is sigma u whole to the power root 1 by n summation capital xi square by summation small xi square. And this is the standard error of alpha hat. So this is another answer, right? Now we are not yet done with the question, so we have only completed the first part of the question. That is you have been asked to estimate the parameters of alpha beta hat using OLS method, which we have calculated alpha hat and beta hat, and just now we have estimated the standard errors of alpha hat and beta hat, that is standard error of alpha hat and standard error of beta hat. Now referring to the second part of the question, here it is said that describe the testing procedure of beta and estimate the 95% confidence interval of beta. So let us just quickly solve this one to end this answer, right? So now that we have beta hat here, so I can write down beta hat actually follows normal distribution with beta as its mean value and sigma u square by summation xi square as its variance of beta hat, right? So now in order to test whether beta is the whether beta hat is the correct or the precise estimate of beta, we have to go for hypothesis testing. Now in case where we have to test the mean with known sigma, then in that case we use tau or z stat, which is equals to expectation of beta hat minus beta hat by standard error of beta hat. This is the value. So this follows standard normal distribution with mean 0 and standard deviation 1. But here we know that beta hat, we know that the standard error of beta hat, that is this, it contains sigma u. So sigma u is actually unknown because it is the standard variance, or if I take sigma u, then that is the standard deviation of the unobserved values, right? So it is unknown. So what is this case? This is actually the case of testing or estimating which parameter? Mean, right? When sigma is unknown. So in this case, we do not use tau test. Instead, we use t test. with n minus 2 degree of freedom. So our test statistics here is t is equals to expectation of beta hat minus beta hat divided by sigma hat u, where sigma hat u is the unbiased estimator of sigma u, and sigma hat u is equals to summation ei square by n minus 2. So we are using this calculated value because we do not know the value of sigma u. So now if I write down my hypothesis, that is my null hypothesis is I have to test whether beta is equals to 0 or not. So since this is not equals to 0, so this is two-tail test. And the t statistics is beta hat minus 0 by standard error of beta hat. Not standard error of beta hat. Here we are using the unbiased estimator, right? That is sigma hat u. Now, so t is equals to beta hat by sigma hat u square. So this follows t n minus 2 degree of freedom. So now comes the part of testing. So null hypothesis will be rejected if the calculated value of t is greater than the tabulated value at the alpha by 2 comma n minus 2. Why alpha by 2 here? Because this is a two-tailed test, so alpha by 2, where alpha is the level of significance. Now, so we will reject it if this is the condition and accept alternative hypothesis, and if it is the opposite, then vice versa. Okay, so now let's write down the confidence interval. So confidence interval at 5% level of significance, that is alpha is equals to 5%, right? That is, the confidence interval is 95%. That means you are 95% confident that the value of beta is going to fall in the acceptance region, right? So how will you write it down? That is t 0.025 n minus 2 less than equals to, sorry, here we have to include the standard error of beta hat, right? Less than equals to the value of beta that we are estimating, less than equals to plus t 0.025 at n minus 2 degree of freedom. So this is the answer. That's all.